Welcome to Brain Vision.
So for part A, let's draw the forces first. So for the system to be in equilibrium, the magnetic force should be upward and equal in magnitude to mg. And the magnetic field is given to be into the plane. So this is magnetic field, and we know that Fp is given by I times L times B sine phi. And this is the magnitude, and direction of Fp is given by right hand rule, which comes from this equation. Sorry, I have to write it in terms of L and B. So we use right hand rule over here, and we see that the current in the bar must be towards right in order to produce Fb upward. So only if the current is in the right direction we will get the magnetic force to be upward, which it should be in order to be in equilibrium, because it needs to be equal and opposite to mg. And we also know that current is equal to voltage over the resistance. And we use so yeah, so to produce a current in this direction, point A should be the positive terminal of the battery, because the current goes from positive to negative. So this side should be positive and this side should be negative. So the current flows in this direction. Now for part B, we will basically use these equations that we wrote over here, including the equilibrium condition where Fp is equal to mg, and this is basically equal to I times L times B, because phi is basically 90 degree, because current and magnetic field are perpendicular, so sine phi is basically 1 here. And from there here we can find the mass to be equal to I times L times B over G. And we can use the equation of I from here in here. So this is going to be equal to VLB over RG, and we solve it and we get the value of mass to be 3.21 kg. So one thing to take a note over here is, if the battery had opposite polarity with A as the negative terminal, then the current would be clockwise and the magnetic force will be downward. But in that case, the system or the battery won't be in equilibrium at all.